Good morning. I am Estivya. I am from 2nd MSc Mathematics. My project title is Reliability Modeling in Human Pathology using Complex Distribution. Now we see introduction, basic definitions, human pathology and numerical example and the conclusion. Now we see introduction. A crucial area of medical science is human pathology, which focuses on diagnosing illness by examining their cellular and molecular causes and effects. However, issues like incorrect diagnosis, inconsistent test results, and unsuccessful treatments still affect the patient care. Next, basic definition, reliability. The probability that a system or component will carry out its intended function without malfunctioning over a predetermined amount of time or under predetermined circumstances is known as a reliability. Mathematical formula is R of t is equal to 1 minus f of t, and R of t is equal to 1 minus integral over minus infinity to t f of x into dx, and r of t is equal to t to infinity f of x and dx. The function r of t is usually called the reliability function, and r of x is the probability density function of the system failure. Next is hazard rate, an essential metric for evaluating an object's dependably in the failure rate, also known as a hazard rate. Hazard rate indicates the likelihood that an object will fail within a specific time frame, or the typical number of objects that fail without a specific time frame. Next definition is uniform failure rate. In reliability engineering, the term uniform failure rate refers to a failure rate that remains the constant over time, meaning that the probability of failure per unit of time remains constant throughout the lifetime of a system. Next, failure distribution, Gombatz. The Gombatz distribution is defined by the probability density function PDF, shortly named as PDF, f of t comma eta comma b is equal to b eta into e power bt, and exponential of minus eta into e power bt minus 1, where t is greater than or equal to 0. Now we see the human pathology problem utilizing the Gombatz distribution with the scale parameter is 1. Since in the place of eta we substitute 1, we get the formula as f of t comma 1 comma beta is equal to b eta into e power bt into exponential of minus eta into e power t minus 1. Next, f2 of t is the formula is 0 to infinity and g1 of x into g2 of t minus x into dx. We substitute the value of g1 of x and g2 into t minus x. We get f2 of t is equal to b square into e power bt into t, and likewise we substitute the value for f3 of t and f4 of t. We get the value f3 of t is equal to b cube into e power bt into t square divided by 2. And next is f4 of t. Similarly, we can substitute the value for g3 of t and g4 of t minus x. We get the value of f4 of t is equal to t cube into b power 4 into e power bt divided by 6. In general, this formula can be written as f m plus 1 of t is equal to t power m into b power m plus 1 and e power bt divided by m factorial. This is a general formula. Next, in case 1, in the case of using two medicines at the same time, the reliability of the system can be represented by R of t is equal to R1 of t plus R2 of t, where R1 of t is a probability of that the medicine 1 performs successfully at the time t. R2 of t is probability of medicine 1 fails before time and medicine 2 is effective at time t. That is, the remaining period is t minus x. R1 of t is equal to integral over t to infinity g1 of x into dx. We substitute the value for g1 of x, we get R1 of t is equal to 2 minus e power bt. Next, similarly, likewise for R2 of t is equal to 0 to t f1 of x into r of t minus x into dx. Substitute the value for f1 of x into r of t minus x, we get R2 of t is equal to 2 into e power bt minus bt into e power bt minus 2. We substitute the value for r1 of t and r2 of t, we get r of t is equal to e power bt minus bt into e power bt. Next, in case 2, R3 of R3 of t is a probability of a medicine 1 and 2 fails before the time and medicine 3 is effective at the time t. R3 of t is equal to integral over 0 to t f2 of x r of t minus x into dx. We substitute the value for f2 of x and r of t minus x. We get R3 of t is equal to 2bt e power bt minus 2 into e power bt plus 2 minus b square into e power bt into t square by 2, and r of t is equal to r1 of t plus r2 of t plus r3 of t. Substitute the value for r1 of t, r2 of t and r3 of t. We get the value for r of t is 2 minus e power bt plus bt into e power bt minus b square into e power bt into t square divided by 2. In case 3, in the case of using 4 medicines at the same time, the reliability of the system can be represented by R of t is equal to R1 of t plus R2 of t plus R3 of t plus R4 of t, where R1 of t is the probability of the medicine 1 performs successfully at the time t, and R2 of t is the probability of a medicine 1 fails before the time and medicine 2 is effective at the time t. R3 of t is a probability of a medicine 1 and 2 fails before the time and medicine 3 is effective at the time t, and R4 of t is a probability of a medicine 1 and 2 and 3 fails before a time and medicine 4 is effective at the time t, and R4 of t is equal to 0 to t f3 of x into r of t minus x into dx. We substitute the value for f3 of x and r of t minus x. We get R4 of t is equal to t square into e power bt into b square minus 2bt e power bt plus t square into b square minus b square t cube e power bt divided by 6. Therefore, the reliability of the system when 4 medicines are used is provided by R of t is equal to R1 of t plus R2 of t plus R3 of t plus R4 of t. We substitute the value for R1 of t, R2 of t, R3 of t and R4 of t. We get the value for g of t is tb the whole square plus bt the whole square into e power bt by 2 minus bt the whole cube into e power bt divided by 6 minus e power bt minus bt into e power bt plus 2. In the numerical cases is in case 1 we consider the different values of time t and failure rate is b. In order to evaluate the system performance specifically, we examine the time values for t is equal to 1, 2, 3, 4, 5 and b is equal to 0.2, 0.3, 0.2, 0.2 and 0.1. We get the numerical value is r of t is equal to, in increasing wise we get this value. This is the graph for this, and in case 2 to access the system's performance in this analysis, we take into account various values of time t and failure rate b. In particular, we look at the failure rate b equal to 0.1, 2 and 0.1. Time values is 1, 2, 3, 4 and 5. We calculate the 2 crucial reliability matrices using the parameter R of t. Following the application of these formulas, we obtain the corresponding values of R of t for each combinations of t and b. T is 1, 2, 3, 4 and 5 and b is 0.1, 0.2, 0.2, 0.2 and 0.1. We get the value of R of t. This is the graph for the case 2, and in case 3, to access the system's performance in these analyses, we take to account various values of the time t and failure rate b. In particular, we look at the failure rate values b is equal to 0.20, 0.23, 0.15, 0.11 and 0.09, and time values of t is 1, 2, 3, 4, 5. We calculate the 2 crucial reliability matrices, mean time to failure and reliability using these parameters. T is 1, 2, 3, 4 and 5 and b value is, we get the value for R of t value, reliability values of various combination of time t and failure rate b. This is the graph for the case 3, and in conclusion, the project concludes that Gompertz distribution is a suitable and effective model for reliability modeling in human pathology. It clearly explains how failure or mortality rate increases with age in biological systems. The model helps in understanding the disease's progression and survival pattern in humans. Reliability parameter estimated using the Gompertz distribution give meaningful medical interpretations. Thank you.